Okay, so previous lecture we looked at the steady mechanical energy equation, and we looked specifically at viscous losses. This was the most interesting part of that lecture, and in particular we looked at viscous losses in the pipe. There were two, one to do with the wall stress and one to do with fittings. And the next lecture we look in much more detail at the pipe friction issue. So to introduce viscous flow, we're going to look at the simplest flow system, which is called Couette Flow, and this is a flow system that is completely dominated by viscous stress. It's the only force in the flow. Okay, so just to try and remind ourselves what we've got, we are going to assume that Newton's law of viscosity holds, and that's the shear stress in the fluid. It's equal to the viscosity coefficient. So this controls the rate at which momentum can diffuse, and this is the rate of strain of fluid. Okay, so we're going to do two things in this lecture. One is to look at the rate at which momentum diffuses, and the next, the steady state condition. And we can summarize that by this slide here. And we've got the bottom wall, which is not moving, and we've got the top wall, which does move. So at time t equals 0, the bottom wall and the top wall are not moving, and the fluid is not moving, and the fluid is not moving. And then at time t1, the fluid starts moving, and because of the no slip boundary, the fluid next to the wall starts moving with the same velocity as the wall. And we know a little bit about this in the sense that momentum diffuses away from this down to here, and when we get to the final case, the steady state case, when there is no more change, we end up with a linear velocity profile like this. Okay, so we are going to look into two things in this lecture. One is the rate at which momentum diffuses into the fluid from a wall, and why we get this linear velocity profile. Okay, so to look at the rate at which momentum can diffuse from a wall, we can solve something called Stokes's first problem, and effectively this is the governing equation. So this sign here, this is the kinematic viscosity, viscosity divided by density, and the problem is a plain wall, and the fluid above it is stationary, and at time t0 the velocity of the wall is 0. And then at time greater than 0, the velocity of the wall is u0. And then what happens is the momentum starts to diffuse into the fluid. And the solution to this equation is summarized by this. So this small u, this is the velocity in the fluid at some point y, so that's the distance above the plate, and at some point in time later, t. Okay, big U is the velocity of the wall, and the solution comes out to be this. We don't need to know how to derive this. This ERF is called the error function, and it's a lookup table a bit like a log is. Okay, and the interesting thing is the rate at which this happened depends on the viscosity and the time. And what the problem looks like, if you imagine that the velocity of the wall has been set into motion at, say, time t0 or 0, and at this particular time, t equals 0.01, this is what the velocity profile looks like, and then at a later time, and a later time, and a later time, and a later time. So you can see the rate at which momentum travels from the plate into the fluid in terms of this solution. Okay, and what ultimately it tells us, so we have some little details here of how you go about calculating these things. I'm not going to concentrate on this within this module. What I want you to take out of this is that the velocity is proportional to the square root of the viscosity. So what this is trying to say is, if you choose a certain point and you want to get a certain velocity at that point, the time it takes is proportional to the viscosity, and more viscous fluids will diffuse momentum at a faster rate. Okay, and this tells you how quickly we get to our steady state condition for Couette flow. Okay, so so we've thought about how quickly we get from this case to this case using our Stokes flow, the first solution to get from here to here, and we know it's a function of the viscosity. And now we want to look at why do we get the linear velocity profile at the steady state condition when nothing is happening. Okay, so classically, how do we approach this problem? We draw a control volume and we do a force balance. So we can make some assumptions here. We've got two very large plates, and the top one is moving and the bottom one isn't. The flow is steady, and nothing is changing in the x direction, the flow direction, so it's fully developed. And there's nothing changing in the z direction out of the board, and there's no pressure gradient. Okay, so we've got a one-dimensional flow, which is just in the u direction, x direction, and we can do a force balance on this. Okay, so here's our control volume, and we need to do a force balance on this control volume, and it's stationary and it's a steady flow. So these forces must balance because this control volume isn't going anywhere, it's not accelerating or anything like that. So we said there's no pressure gradient, so there's a pressure on this side of the face and there's a pressure on this side of the face, and they're both the same. So there's no net pressure force making this control volume go to the left or the right. And there's a force on the horizontal planes due to the fact that there's a stress, because we know that there's a velocity gradient, and there must be a velocity gradient because this is the wall velocity and it's non-zero, and this is a stationary wall, so the velocity's got to be changing in some way across this gap. Okay, and we know what the stress is. We can assume that it's a laminar flow. So if we want to work out the stress at the bottom here, we can say it's the shear stress, and if we want to work out the force, that's the shear stress times the area, and the area in this case is dx times the width coming out of the page. If I say it's unit width, then we've got dx. Okay, so we know that the shear stress at y, which is this point here, that's mu du dy, and we don't know what the shear stress is at this point, but we can use a Taylor series to make an estimate as long as our control volume is small. So here's the implementation of the Taylor series, and then we just substitute this tau of y here, tau of y here, so we end up with this term here and this term here. And because it's a force balance, and because these forces must be equal, effectively the shear stress at y must equal the shear stress at y plus delta y, which gives us this set of information. Okay, so here's my force balance over my CV. I've said that the pressure forces are 0, so I can say that this term is equal to this term, and the du by dy cancels out, and I can also cancel out the viscosities, and I end up with this governing equation. So I hope you appreciate why we needed to talk about Stokes' first problem, because the steady state solution has no effect, well, the viscosity has no effect on the steady state solution. It only controls the rate at which we can get there. Okay, so if we want to find out the velocity profile, we need to integrate this twice, so second order ODE, So we've got two integration constants, A and B, and we've got two walls, so we can apply two boundary conditions. So the first one, we can apply the boundary condition at y equals 0. So at y equals 0, we know that the velocity is equal to 0. So this term is equal to 0, and this term is equal to 0, so therefore b is equal to 0. And then we can apply the other boundary condition at y equals h, and at y equals h, we know that the fluid velocity is the wall velocity. Okay, so u wall is equal to a times h, we know that's 0. So therefore a is going to be equal to uw divided by h. Okay, so we put that back in and we generate our velocity profile, and that gives us our linear velocity profile between these two things. Okay, and let's think about why this is. So we said that there's a stress balance in the fluid, and there are no other forces. So effectively, what's got to happen is the shear stress in the fluid is going to be constant, because effectively the fluid wants to spread the load out, and it spreads the load out by enforcing a linear velocity profile. Because if the linear velocity profile is this, if we take this equation and we differentiate it to work out du by dy, we can work out what the shear stress is and the force. So this is the force that you have to apply to the plate. Okay. Okay, so nice simple introduction to viscous flow. If you want to find more about Stokes' problems, have a look at this book. And next lecture we start looking at pipe flows, where we've got a pressure gradient.